Good afternoon, and thank you everyone for coming. Uh, my colleague Eric and I are going to share the story of how we scale machine learning at Yahoo. Here's a little outline of what we'll do. We'll first talk about challenges in large-scale machine learning, how bringing together parameter server and Spark can help overcome some of these challenges, visit a couple of example use cases, and finally conclude by describing how all of this works seamlessly on our Hadoop cluster. So let's talk about learning at web scale. As you know, in Yahoo, we don't just have big data, we also have huge models. As an example, our Yahoo Word2Vec application has hundreds of billions of parameters and about 500 billion samples. At this scale, distributed training is pretty much necessary. And if you want to hold the model in memory, you probably want to distribute it in a bunch of different nodes to store portions of it. And you probably want different training workers that can process different partitions of the data, right? Let's look underneath and see what can actually enable something like this to happen, because you need to synchronize huge models between all these workers. So what I show here, every row corresponds to an example, and in a lot of applications, it's extremely sparse. And this was pretty much the theme of the previous talk, that you can leverage sparsity and enable web scale learning, at least for some algorithms. So as long as you have a mechanism where you work with one example at a time or small mini batches of example at a time, you're good to go, because you're only synchronizing small portions of a model at a time, right? So in terms of solution strategies, there are two popular optimization methods that you can use to build a model from all your examples. You could take a batch style approach where you look at all the examples and then make one update to the model and repeat this for a few epochs. Or you could take a sequential or an incremental style where you react to every example or every small batch of examples, right? And stochastic gradient method would be a good example of a sequential approach, and batch gradient descent or LBFGS is a good example of the first. Now, both the styles have their pros and cons. For instance, the batch method converges fairly quickly, requires only a small number of model updates, but every epoch can be very expensive because you're looking at all the data. On the other hand, if you take the sequential approach, while the convergence rate is not as good, it's a great fit for big data because often one pass is enough. And it's inherently sequential, so it's a challenge to do it in a distributed fashion. Now, if you're building a system for it, then you probably want to be able to support both batch and sequential optimization to support a large number of use cases. And to do sequential training really well, your architecture must be able to handle frequent updates to the model. And because batch training requires hundreds of passes of the data, each pass must be very, very fast. Now, a scalable architecture for supporting something like this is the so-called parameter server, which was first introduced in Yahoo for large-scale LDA. There have been numerous refinements since, particularly I'd like to call out Google's disbelief, and then some academic implementations as well. The key idea is the parameter server is simply a distributed store for storing the parameters of a machine learning model. You could think of your model as a large dictionary of keys and values, and basically you shard them by keys, store them in different nodes, and then this is sort of an abstraction for mutable state that you can very frequently update. So in a typical mode of operation, clients that don't talk to each other fetch the portions of the model they want by looking at their mini batch, process it, do some kind of sparse update back, right? And that's pretty much all there is to parameter servers. Before we talk about how we bring the parameter server technology and marry it with Spark, let's talk a little briefly about why Spark alone would not be sufficient for our scale. As you know, Spark has these JVM instances called executors and little lightweight threads called cores, which are the actual workers, which can't talk to each other. So you pretty much have to go via the driver. And a typical optimization library like MLlib, the driver holds the model, and you do something like this loop. This is just pseudocode. Broadcast doesn't have that syntax, for example. So you typically broadcast the model from the driver to the executors, which read a portion of the data, compute the gradient, and report it back to the driver, which then updates the model. So you do this in a sort of a stage-wise fashion. This has obvious limitations. The driver should be able to hold the model, and it's not a natural fit for sequential because sort of going through the driver limits the frequency of model updates. You can circumvent that to a small degree by having a very large mini batch size, but then your convergence rate would suffer. Also, perhaps surprisingly, even for batch methods, this may not be a great fit when you are dealing with web scale, because the driver's bandwidth can become a bottleneck. And notice that in this style of operation, you're not pipelining things the way Spark likes to pipeline a lot of other things. For instance, you do computation of the gradient, and then you update the model by tree aggregating, which is just a fancy reduce, right? This also limits the throughput, and you can't get fast enough epochs. So clearly, the parameter server architecture load balances this nicely, allows a good abstraction for mutable state, and circumvents both the limitations. So we decided to combine both of them. We want to leverage Spark for HDFS input-output, all the fine-grained load balancing, failure recovery, in-memory operations, and so on. And we want a parameter server as a means of synchronizing the models. So this schematic that I show here is the same as what I showed a couple of slides ago, except the clients now sit on top of Spark cores, right? And it's just combining two abstractions, Spark for distributed execution and parameter server for shared mutable state, right? So let me call out a few salient features of Yahoo's homegrown parameter server. First, this was implemented in Java and Netty by Andy, who's sitting right here. And we also have Scala wrappers. This allows seamless integration with Hadoop. So when you deal with Java, you want to be very careful about GC, and we take care to make sure that there is absolutely no garbage collection and steady state. And this is possible because in most machine learning applications, you can at least determine the number of features in advance, decide what you want to put in them, and pre-allocate the arrays. So it's essentially key value store. All the operations are done in memory. We have the ability to lock on a per key basis or operate in a completely lock-free hog-wild fashion if you want. We allow both synchronous and asynchronous operations. We also have an abstraction for distributed matrices that I will go in detail, which supports linear algebra primitives. Because this is all written in Java with excellent integrations to Hadoop, we can checkpoint state of the parameter server directly to HDFS, export the model, and we also support user-defined functions where the client can, so let's say you want to process something in the parameter server, you want to make a small change. You don't want to fetch something, process it, only to push it back. So it would be nice to have sort of map-reduce abstractions on it, and we provide them via user-defined functions. So basically, our API looks like this. This is just a key value store. You have your usual gets and puts. And in addition, we have multi-get and multi-put. So if you're working on mini batches in machine learning applications, the keys could correspond to the feature IDs that are present in that mini batch. We also have the map reduce that I alluded to in the previous slide. A lot of these operations, you will notice return a future, which means as a client, you have the freedom of deciding whether you want to operate asynchronously or block on the future. The matrix abstraction that I just talked about extends the map abstractions, provides all those gets and puts and so on, but also provides a limited number of BLAS operations like dot product, scaling, and so on. And we also have special support baked in for sparse vectors. So let me talk about a couple of examples. I will talk about a batch use case. As you know, Yahoo makes its money primarily through advertising. So when you go to yahoo.com and search for Apache Spark, you not only get the results that you want, we also show you an ad that we think you might like. The way we do this is we sort our candidate ads based on a product of the bid by the advertiser and a probability that we think you'll click on it. And so accurate determination of this click probability is critical for this auction process to sort of work. And a simple example of such a click model would be something like logistic regression, where you can posit that the log odds of the ratio that you click on it versus you don't click on it depends linearly on some features that you derive from the query, the user, the advertisement, and additional context we have, right? And when you optimize this model, we want to be as faithful to the training data as possible. And things like batch methods like LBFGS are often very preferred. So let me do LBFGS just enough background in one slide to understand our implementation. As you all know, you can do a lot better than gradient descent by incorporating curvature information and doing Newton's method, except that it's impractical because it wants you to invert this giant matrix. So this matrix called the Hessian matrix incorporating all the curvature information can be very large. If you have billions of features, this is a billion by billion matrix, which is difficult to store, leave alone invert. So you do the best trick in computer science, you approximate it. And the way you do that depends upon previous values of gradients and the differences in the model that you've stored. Here is the algorithm, Nochadal's famous double loop algorithm. I'll give you about 2 seconds to process it. No, really, all I want to show is that it depends on a bunch of state vectors, which are the gradient vectors and the previous model differences. It'd be nice to store them in a distributed fashion. And it involves a bunch of vector math on it. And that's it. That's all you need to do in order to do the Hessian approximation. Next, because you're doing things approximately, you have to be very careful about computing the step size, which requires a pass over the data as well. And that's pretty much LBFGS. It's just approximate Newton's method. So with that background, let's look at our implementation. You have all the state vectors that are distributed across the parameter server shards, as opposed to a conventional parameter servers where you would shard them by key. Here you store different subsets of the columns on different parameter server shards. And I will tell you why in a moment. So in the first step, the executors read the data, compute the gradient, and push those sparse gradients that you heard about in great detail in the previous talk onto the parameter server. And then once this is ready, you have all the state that's necessary for doing the actual LBFGS math, which is done directly using the parameter server. So the reason why we do column partitioning for this is because when you want to do something like dot product, you don't want to copy vectors across the shards. When you do a column partitioning, that is when you store subsets of these vectors in different shards, you can do individual dot products and combine them. And that's pretty much the key. Then once you have the search direction, you do another pass on the executors, which computes the losses for various step sizes, reports them back to the driver, which then updates the model. And that's it. You cycle through these 4 steps over and over again. And in order to make all of this work blazingly fast, we incorporated a bunch of tricks as well. We intersperse communication and computation, as I commented before, because we have this increment and fetch operations. We have a few tricks for quicker convergence. We borrowed some ideas from Bhopal Babbitt. We do parallel line search. With, the cost of line search is amortized for all the different step sizes that you can try. You just do one pass over the data. We try to reduce network bandwidth whenever possible by using compression. If you have binary data, completely throw away the values. And we use matrix math. We use compressed parse row matrices and do operations directly on a mini batch. As a composite effect of all of this, for a modest sized 100 million feature example, we can do one iteration in about 22 seconds, whereas MLlib for this use case takes about 40 minutes. I mean, admittedly, the architectures are very different. It's not a fair comparison. But that's all I have about LBFGS. Let me invite Eric, who is going to talk about word embeddings at scale and a very beautiful application of that. Thank you.
Thank you, Badri. So I'd like to talk about another application that we have implemented on top of our Spark plus parameter server platform, and specifically a scale-up of word embeddings. So word embeddings is a technique from natural language processing involving taking an input corpus of words and determining a set of vector representations of words in that corpus that in some sense capture the meanings of the words through the geometry of the vectors. That is, you'd like, for example, vectors for words that are semantically similar to be kind of nearby within the vector space. Most of these algorithms operate on the corpus in an unsupervised fashion. That is, there's no injection of semantic significance or relatedness into the algorithm specifically. They extract that purely from the order of the words within the corpus. The set of words for which vectors are learned are referred to as the vocabulary, and I will be referring to that later. A few years back, this paper appeared and kind of shook up the field a little bit, and it introduced some new techniques for computing these word embeddings under the moniker of word-to-vec. And they also showed that the vectors learned by these techniques have some new and surprising properties. In addition to having this property of related words having nearby vectors, they also showed that their vectors can be used to solve analogy completion problems, kind of like what they had on the SATs some years ago, by doing purely, very simple vector addition and subtraction using the vectors for the words that are known in the analogy problem. One of the algorithms in this paper that we're interested in for this talk is called the skipgram with negative sampling. And it works roughly as follows. So the input corpus is processed to create pairs of words where each word in the corpus is paired up with its neighbors. And then for each such pair, additional pairs are generated where the second word in the pair is selected at random from within the vocabulary. And these latter set of pairs are referred to as random negative examples. So the algorithm then proceeds to determine actually two vectors for each word in the vocabulary. A so-called input vector, here denoted by bold U, and an output vector denoted by bold V. So that the vectors have roughly the property that the dot product of the input vector for one word and the output vector for another word, W prime, is discriminatory in terms of whether that pair of words occurs as a bona fide pair of neighbors or as a random negative example. And specifically, we would like that the sigmoid, this well-known nonlinearity, applied to the dot product is close to the probability of a pair of words occurring as legitimate neighbors versus random negative examples. And if a pair of words doesn't occur as either negative examples or a pair of neighbors, it doesn't figure into the training at all. Stochastic gradient descent or mini-batch stochastic gradient descent is used to train the vectors, and sparing you a lot of details, it basically involves computing a lot of vector dot products between the U's and the V's for the various word pairs, and then updating these vectors per some vector linear combination operations where the coefficients in the linear combinations depend on the dot products. So some researchers at Yahoo had the idea of applying this algorithm to this type of data. And what you see here is a user search session comprising queries entered by the user, here denoted in purple, and search result hyperlinks clicked by the user, denoted in gray. And then the user also clicked on some ads. And the search session captures the order in which these actions were taken. And there are literally hundreds of millions, if not billion, of these search sessions. So the researchers had the idea of learning vectors for what you could call generalized words, that is, entire queries, hyperlinks, and ads appearing in this type of data set. As you can imagine, this application involves vocabulary sizes that are quite a bit larger than sort of the more conventional applications of word-to-vec on more traditional corpuses. So the researchers tried out their idea using a special purpose large memory machine with single machine implementation of word-to-vec. And we're able to train about 90 million words or so, and found that the idea was pretty promising. Oh, and the way the vectors would be used would be to, for example, find more relevant ads for a given query, for example, if the query occurred sufficiently frequently, by doing nearest neighbor computations in the vector space involving vectors for queries and ads. So they tried this out in a kind of, as I said, a smaller scale, and found it to work reasonably well, but recognized that in order for the idea to really hit its potential, they needed to be able to scale up the vocabulary. This is where we came in, and specifically they wanted a system that could train 200 million 300-dimensional word-to-vec model, skip-gram with negative examples, using mini-batch stochastic gradient descent. And this is what essentially we implemented, a system that could do this using the Spark parameter server platform, and specifically with the matrix flavor of the parameter server that Badri had described earlier. Some of the key aspects of our system is that it's very network efficient. The vectors never actually go over the network, and I will show you in the next slide how that's done. And moreover, most of the compute actually occurs on the PS server shards. This is somewhat of a twist or a non-standard use of the parameter server technology with respect to what's out there in the literature. So this is how our system works. This diagram is similar to ones that Badri had shown earlier. On the top, we have the parameter server shards, and on the bottom, we have the clients or learners that would be deployed using the Spark API. So one of the twists that we have on the basic parameter server paradigm is that rather than sharding the vectors by vocabulary word, we shard them by component. So in other words, every parameter server shard stores a portion of every vector for every word in the vocabulary, rather than the vectors for some subset of the words. And this has a lot of advantages, and we will see that as I describe kind of the processing. So the first step in the processing is the clients read in data from HDFS and compile these pairs of words and neighbors that I had mentioned earlier, and communicate or broadcast the indices of those to each of the parameter server shards, along with some seeds for random number generation. Then the parameter server shards will use those seeds, which are the same for each shard, to generate the random negative examples that I had mentioned, and then compute partial dot products for the portions of the vectors that they store. They then send the partial dot products back to the client, which then sums them up and applies the nonlinearity, the sigmoid, in order to determine the linear combination coefficients needed for updating the vectors. It then broadcasts this coefficient back to the shards, which then update the vectors, portions of the vectors that they actually store. And in this manner, all the vectors don't actually move. The only communication involves indices of words and partial dot product results and these coefficients. This multi-stage computation I just described occurs in parallel. There are several copies of it occurring, actually, hundreds, many hundreds occurring in parallel, multiple threads, both in the client and the server, over hundreds of millions of mini batches in the training set. So as a result of this kind of network efficient architecture compared to conventional PS system that would get and put the vectors and do the math on the clients, we save quite a bit in terms of network. We can train a 200 million word vocab with very large data set in a reasonable amount of time. And when we deployed this system, the business metrics look very good, even in comparison to the single machine, smaller scale system that was implemented. And as a result, it's been put into production with regular training at Yahoo. The team has implemented several other applications on top of our platform. Specifically, we have a large-scale online learning platform for supporting models with hundreds of billions of parameters. More recently, we've worked on a factorization machine application on our platform. Hopefully, some of us will talk about that in the future. Let me say a few words about how we, the mechanics of deploying this system on our Hadoop cluster. So we have our training data on HDFS, and we launch the parameter servers using the Apache slider application. After we tell it how many shards we want and how big each one should be. We then programmatically extract the host names and ports that the server shards are listening on and pass that into the Spark command line, which then launches the clients. They then interact, pull in data from HDFS and interact with the parameter server shards to carry out the training. And when training is done, the model can be exported either by the parameter servers to HDFS or pulled in by the clients and stored in HDFS in a perhaps even more distributed manner. So in conclusion, we've explained how parameter servers are indispensable for training large models. We explained how combining Spark and parameter server technologies has helped us with our scale-out problems at Yahoo. And we also explained kind of a twist on the usual parameter server paradigm where there's a lot of compute and kind of a non-traditional layout of the model across the shards. Thank you.
Thanks very much for Eric and Badri for this great session. We've got a couple minutes for questions, so if you have a question, please come up to the microphone here and ask your question away, please.
Hi. I want to know if when the workers send the gradients to parameter server, how do you combine the gradients? I mean, do you calculate some kind of averaging, maybe?
So are you talking about the LBFGS implementation? Or?
Yes, or the...
So in the Word2Vec, those threads that I talked about, I explained one. The updates from multiple threads occur asynchronously, lock-free, in a hog-wild manner.
In the mini batch example, for instance, is a kind of instability if you average over, I mean, all the workers or the or kind of moving average.
Mm-hmm. We don't do any averaging for that application. If you're familiar with the Google open source implementation of Word2Vec, it's kind of, we do kind of a similar math for the gradient aggregation.
Okay.
But distributed across multiple machines rather than within a single machine.
I have a question. So some of these algorithms you are actually running on CPUs, right? Like Word2Vec, I think, is it much better to run it on GPUs? Is it like the next step, is it easier to port some of these techniques to GPUs?
So we haven't looked too much into that. One kind of thing we focused on with this particular application is to be able to run in a commodity data center as it stands today. So CPU was definitely part of that. GPUs have the problem of more limited memory than full server can offer, and the challenge there is how you shuffle data in and out of that memory. And with a very large vocabulary in that particular application, it's not so obvious how one could leverage GPUs, but certainly something that we keep thinking about, and hopefully we'll make progress on it.
All right, that's it for time. So thanks for Badri and Eric for their session.